Okay, so I want to add one thing to our inverse trig function material. So I'll give you a second, go to those notes. It's funny that it feels like every time I teach this course, when I do that section, I forget this piece of information and then do it after the exam. It wouldn't have influenced the exam anyway, but it involves the arctan function. So if I think about the tangent function, one cycle, pi over 2, negative pi over 2, okay? And I think about the inverse, or I'm going to call it the arctan. Recall that we can find the graph of an inverse function by reflecting the original over this line. In fact, I'll draw it, that line. So if I were to do that, I get this shape. And the point of that, a little sloppy there, is this. This is information that comes up in multiple types of problems. And the information is this, that the end behavior. Okay, so as arctan goes to infinity, this is a horizontal asymptote at pi over 2. Okay, and then likewise, I didn't leave myself any room. I apologize. Oh, let me try to fit it in here. Sorry. As x approaches negative infinity, let's write it like this. Same thing. Approaches negative pi over 2. So this is valuable information. Let's just memorize this as fact. You don't need to recreate this or anything, but this will come up. Okay, so I want to throw that in there. I left it out. I didn't need it, but we're good. So what we're going to do is move on to the last section of 6.8, which is about what we call indeterminate forms and involves something called LHopitals Rule. So I want to show you a couple old problems from like Math 140, limit problems. So let's let x go to 1. So this is what we call a rational function. And if I substitute 1 in, I end up with 0 over 0. Okay, so we've seen this before. So as x goes to 1, the numerator goes to 0. Likewise, the bottom goes to 0. So there's different techniques. We can divide everything by x squared. Well, actually, it's not. That's what I just said was incorrect. We factor. So the idea here is right, and these are the zeros, right? This is 1 minus 1, this is the 0. This is the 0. They're canceled out. So I've gotten rid of the zeros. I pop the 1 in, I get a half. There's also, yeah, leave it at that. So the point being this, the top and bottom, if the top is going to 0, that has the effect of making the whole thing smaller. If the bottom is going to 0, that has the effect of making it larger. So you have these competing effects. That's what an indeterminate form is. This function, this limit, takes the indeterminate form. Indeterminate. It's kind of hard to say. Okay? What that sort of means, it's a long-winded way of saying sort of unknown behavior, right? 0 over 0, that doesn't even mean anything. It's nonsense. So it's you can't really see what the limiting behavior is. So you go through this process to find out. Okay? So that's an old problem. You may have heard this phrase, indeterminate form 0, 0. Let x go to infinity. Okay? So as x goes to infinity, what is the numerator doing? It's going to infinity. That has the effect of making the entire thing get very large. As x goes to infinity, the bottom goes to infinity. That has the effect of making the entire thing get smaller. So you have, again, these competing effects. So the typical, there's a couple shortcuts you can use. You can compare degrees. These match up. So the limit would be the leading coefficients 1 over 2. That's the nice shortcut. Use that shortcut. Or you can divide everything by the highest power. This is what I was saying before. If I divide out everything by x squared, what I'm doing now is changing infinities to zeros, right? I'm getting zeros out of the process. These are zeros. That goes to 0. That goes to 0. Goes to a half, right? Leading coefficients as well. Okay, so the point being, though, this is another indeterminate form. Indeterminate. Infinity to infinity. Okay, and I guess I should add this. It doesn't. I shouldn't get fixated on one sign. Positive and negative both applies. Okay, and my phone is ringing, so let me just stop quick. I'll be right back. All right, I'm back. So when evaluating limits, what we just did or what I just did on the last 2 sheets is totally legitimate, right? But we like shortcuts. So this is LHopitals Rule. I know there's an apostrophe in there, but I just don't get down with apostrophes. So, okay. It's a little bit wordy, I guess you could say, as most theorems in mathematics are, but it's actually pretty simple. So, a couple disclaimers. 2 functions or expressions, differentiable, near some value of a. To be more precise, you might say in a neighborhood of a, which means a non-zero open interval, but this gets the point across. Also, g prime of x cannot be 0. You'll see why in a second. Okay, so this is just sort of the fine print. So the rule states that if, and let me write it out and I'll talk about it. We're going to take the limit as x approaches this value. I might have to do this on 2 pages. Okay, so if you have this situation, and this will make sense in a second, or f and g both go to 0, or f and g both go to infinity. All right, one of these 2 cases, this case or this case. No mixing and matching here, okay? This case or this case. And notice again, the sign is not really part of the deal. I'm going to go back to this, so let me just put this here. In fact, let me do it like this. Then, so if this is the case, then let me write it out. Okay, so what does this mean? Well, if I look at this situation, f over g, the first example I did, it was exactly this, right? The top was going, I'm calling the top f, that went to 0, the bottom g, that went to 0. Okay, we went through a factoring process to find the limit. This is telling me that I can do this instead. I can find the limit of the function by taking the derivatives of the top and bottom. Okay, we'll see some examples. This is usually much quicker, much easier, and much cleaner than some of the algebraic processes that we go through to find limits. As well, in the second example I did, you had an f and a g, a top and a bottom. They were going to infinity. That was this case. So it's this case or this case, do this. Okay, very useful. A lot of students I find already know this. They had calc in high school. I think it's taught earlier along the path in high school than it is typically at this level. I think my gut feeling is that maybe we're trying to emphasize the algebraic processes the hard way, right? First, but what do I know? Let's see some examples. So we're going to find the limit. I'm going to do some right out of the text. Let's see, x minus 1. Okay. So if I were to direct substitute, the ln of 1 is 0. Excuse me. 1 minus 1 is 0. So this is, in fact, going to 0 over 0. I'm just going to write this. This isn't really part of a solution, but just for your notes, maybe. Okay, so in fact, with one like this, there's not really algebraic tools to play with this. This is not going to factor, obviously, right? So this is kind of stuck. This might be one where you really have to use this. So what do? Well, this limit will be the same as the limit of derivative top bottom. X 1 minus 0. So I'm sorry. I'm just going to scratch that. This is 1. Right, sorry. And now I have 1 over 1. I have 1. Okay? So real clean, real easy. Let's see a few more. About limit x go to infinity, e to the x, x squared, they got. All right, so as x goes to infinity, we know e to the x goes to infinity, and certainly x squared. So this is this indeterminate form. So we'll apply the rule. Again, I'll take derivatives of top and bottom. One thing I want to point out, this is not the quotient rule. I am not in any way implicating the quotient rule here. I'm taking the derivative of the top and I'm putting it over the derivative of the bottom. Okay. Well, now as x approaches infinity, the top is going to infinity and the bottom is still going to infinity. So it didn't seem to work. Well, what do? We just do it again. So you could do this 100 times in theory. Okay, I've gotten rid of the x out of the bottom, so e to the x clearly going to infinity. It's over 2. Okay? Pretty easy section. I don't like the word easy, but not too difficult. I want to point a couple things out, and that is, let me think of an example. Let's go to infinity. Give me a second. I got to think of an example here. This is kind of a silly example, but it gets the point across. I don't think you would ever see an actual problem built like this, but this is the point. The top here, e to the x, is going to infinity. E to the negative x is going to 0. So the top and bottom are having the same effect. The top is making this grow very large. The bottom is making this grow very large. This problem is over. What people sometimes do is they see anything with a numerator and a denominator and a limit, and then they automatically invoke LHopitals Rule and make a mistake. So always check, right? We always check these things out first. This is not an indeterminate form. This is tending to infinity over 0. All right. 0 over 0, excuse me, or infinity over infinity, plus or minus. Okay? One other thing I want to point out. There are other indeterminate forms, and go back to what that means. It means the behavior is disguised. Okay, so I'm just gonna, there's a few, I'm gonna mention 2 that are somewhat common. In fact, I'm gonna do another problem. And I'm gonna abbreviate because I'm sick of writing this word. One indeterminate form is when you have, and this is sort of abusive notation, but when you have 2 things that are multiplied, and one is going to 0, and one is going to infinity. And if they're multiplied, this obviously is making it small, this is making it large. You have this competing behavior. Who wins? You don't know. You got to dig deeper. The 0 could be dominating, sending the whole thing to 0. The infinity could be dominating, sending the whole thing to infinity. And another common one, I'm going to do an example with this one just so you can see it. That's infinity. It's a little sloppy. Sorry. Minus something goes to infinity. Right? Again, are they sort of growing at the same rate? Is one of them dominating? Is this one dominating, therefore making it large positive, or vice versa? You don't know. It's disguised. So I'm going to do a quick example of something like this to see what you would do. Let's do this one. This is right out of the text. X goes to 0 of tan x minus x, which is clearly going to 0, over x cubed. I see. All right, so they're both going to 0. 0 minus 0 over 0, everything's going to 0. This is not the problem I want to do. Yep. I'll do it anyway. This does not really apply to this. In fact, you know what? I don't even want to do it. I want to do one that keep this rolling. I want to do one that applies to this. Sorry. I'm not editing any of these videos. None of that. Okay, this one's better. This is what I wanted to do for you. Let's let x go to pi over 2 from the left. And the function is secant minus tangent. Okay, so if you recall, let me just work over here a bit. We know what tangent does, right? Pi over 2 left. So this is going to, I'm just going to put a little note here. You wouldn't show this on a real solution. This is going to infinity, right? What about secant? Well, secant's 1 over cosine. So secant, this is cosine. Secant looks like this. Asymptotic behavior at pi over 2 as well, also going to infinity. So here we have this indeterminate form. Infinity minus infinity. Which one's winning? We have no idea. So I can't apply L'Hopital's rule clearly. This is not a quotient. Is there anything I can do? Well, let's try pull something out of our sleeve here. What's secant? Well, 1 over cosine, right? What's tangent? Sine over cosine. So fortunately, I have a common denominator. 1 minus sine over cosine. Okay, now if I direct substitute, this is just a rearrangement of this. This is still going to 0 over 0. Well, it's a new indeterminate form. This is going to 0 over 0. This was going to infinity minus infinity. But this is an indeterminate form where I can apply L'Hopital's rule. So I can't apply it here, not necessarily here as it stands. This one I can. So this will be negative cosine over negative sine. Does that look right? Let's cancel these guys out. And what do I have now? This goes to 0, this goes to 1. So the limit of this is 0. Okay? Oh, sorry. Didn't realize that I had moved this. Let me just do that for you. Okay, L'Hopital's rule. Like I said, it's a nice light section for you to get back on track after the exam. Okay?